Welcome, I'm David Pommerenke. I'm a professor at the Institute of Electronics at Graz University of Technology, and we teach and research electronics and electromagnetic compatibility. In a previous video, I showed the shielding effect for plane waves. In plane waves, one doesn't have to distinguish between E and H field. This video is about shielding at lower frequencies. Usually at lower frequencies one has to distinguish between E field shielding, electric field shielding and magnetic field shielding. So we have prepared a setup here. We have two coils, a current is flowing, they are magnetically coupling, and we can insert different materials, and what we're observing is the coupling from one coil to the other. We do it on this network analyzer, and we go from 100 kilohertz to 5 megahertz, and we set it to 3 dB a division. Between the coils we can insert different materials like a ferrite, another ferrite, a metal plate, a metal ring, and other materials. Besides the magnetic coupling experiment, we have an electric coupling experiment prepared. This will be due later, but here we'll of course interact or emphasize on the importance of electric field shielding, while this is for magnetic field shielding. Right now in the network analyzer we see the coupling. The coupling at lower frequencies goes up, and later it decays. It decays because simply the inductance of the coil is so high that the current diminishes. Now we can insert different objects or do different experiments. For example, if I rotate this by 90 degrees, we saw the signal massively goes down. The reason is simple, because the magnetic field which goes this direction, if the coil is like that, doesn't induce a voltage. So we go back, and I put it in a memory trace. Now let me explain a little bit about material interaction with respect to electric field. We're talking about very low frequency, maybe electrostatics, or not very high, not gigahertz. Now what I show here is a microstrip, so a piece of metal here, a ground, and we have electric field lines, a typical structure of electric field lines shown. Maybe not perfect, but shown. Now I want to ask you, what is an electric field line? What does it signify? Is it a line of constant field strength? No, it's not. Or is it a line of constant potential, constant electrical potential? It's not. The electric field line is a line of force. It shows the following thing. Let's say we put an electron here, and here is the electric field line, then the electron would experience a force in this direction. Think about, we have a charged object here, and there's ground here. This is on some voltage. Yeah? Now, let's say we put an electron here, it would feel a force here. Or if we put an electron here, it would feel a force here. So if we connect all the lines, the vectors of the line of force, we will get the electric field line. So electric field line is a line of force. A magnetic field line is a line of force, but we don't have magnetic monopoles, so they cannot move. Let's do a Gedanken experiment. So think about, we have a metal plate at 0 volt, for example, and a metal plate at 100 volt, and we just show homogeneous field lines, and we don't show fringing fields, so these are infinitely large field lines. Now we will move an object, a conductive object, slightly conductive object, into here. So now we moved this object, a slightly conductive object, a cylinder, between the two plates, and I still only show the electric field lines which were there before we moved it in. It's conductive. What does conductivity mean? Conductivity means there are free charge carriers. So think about the following situation. We would have an electron here, and there's a field line like here. So what would happen? The electron would feel a force in this direction. Now imagine a couple electrons which all can move, and let us see what these electrons will do. So now we have our plates and the electrons, and an electron will move until something happens. The electron will move until it hits a boundary, so it may move to the wall. And if an electron would be here, and there's a tangential field line, then the electron would still feel a force. So the electrons have to reach the edge, and there can only be a field line in this direction, otherwise they would move sideways. Now, one could say they all end up here, but the situation is more complicated. We have again an initial field, and then we have a field from the electrons. So the real field is a superposition of the fields from the electrons plus the excitation fields. So we come up to a situation where there's our slightly conductive cylinder. We have charge carriers here on the outside. We have charge carriers here on the outside, and the total field sums up. So the field from the charge carriers and the fields from the external sums up that the field lines are perpendicular. So there cannot be a tangential force, otherwise the charge carriers move. There cannot be any field inside because the charge carrier would move. And the consequence, if there's no field inside, the whole inner volume is 100% shielded. This was an example for very low frequencies. Now, what happens if the frequency goes higher? Think about if it's sometimes plus and sometimes minus, minus plus, it changes. The charge carriers have to move to re-establish the boundary conditions such that they're on the surface and they're perpendicular. So how fast does it happen? And this, to understand this, there's something which is called the relaxation time. It's epsilon divided by sigma. It's like RC. And that tells us how fast can they move. And this is in metal a very, very fast number. It's like pico or femto or attosecond. So for metal, we can say that the redistribution of charge carriers of the fields happens with the velocity of light. Now, if we would take a piece of wet cardboard, then we would see good shielding at DC. But the higher the frequency goes, the lower the shielding is because the movement of the charge carrier simply isn't fast enough. I want to emphasize on the importance of low impedance current flow path for the eddy currents which are induced, otherwise no shielding is achieved. This is a metal plate in styrofoam. Later for the other experiment we'll see why I put it in styrofoam. If we put the metal plate in here, we see the field is strongly reduced. So what happens? The magnetic field causes a current here, a circular current, the eddy current. This current causes a field, and now this coil can see the original field and the reaction field. Now they cancel each other quite well, so we achieve a lot of shielding here. Now let's use another piece. This is a cloth, and we already used it in the other video. It's an impedance cloth. It has an impedance of 377 ohm square. Ohm square means if you cut a square here and measure the resistance or impedance from here to here, you get 377. If you cut a bigger square, you will again get 377 because the width increased and the length increased. Now if we put this in between, the magnetic field penetrates it and causes an eddy current. But we see absolutely no effect because the reaction field is too weak. 377 square ohm material inside the magnetic path has pretty much no effect. And in the plane wave shielding, we have seen that the field reduces the plane wave by about 6 dB because of the impedance of free space. Next thing we could do, for example, we hold a metal ring in here. This metal ring has a gap. So I hold the metal ring in here and nothing happens. What happens? Why doesn't it shield? Well, the magnetic field penetrates the ring, it induces a voltage here, and there's a gap. So there will be a voltage across the gap, but there's no current flowing because there's a gap. If I close the gap, we see the coil reduces the field. Open, close, open, close. So what happens? The magnetic field penetrates here, induces the voltage, and if the gap is closed, a current can flow. And now we come back to the same concept we used in the other class, or the other video. That is, this coil receives the field from here, but if we put this in, there's a reaction field. The reaction field is caused by the current which is induced here, and now this coil sees both fields. It sees the initial field and the reaction field, and they are out of phase, so this reduces. Now let's put some other materials. For example, this is a ferrite. Ferrite has a high permeability, and if we put this in here, we see the signal going massively up. The reason is the magnetic field is guided within the ferrite to the other, and that's why the coupling increases. Let's take a ferrite plate. This is a plate of ferrite. The fact that it has a hole is not important. If I put it in between like that, it has pretty much no effect. But if I put it in this direction, it increases because it guides the field. An interesting aspect is what happens if we put two plates behind the coils. We see a small increase of the coupling. The reason is that the magnetic field, which without the ferrite goes back here, suddenly finds the much more favorable path to flow inside here, which increases the field strength here, and that increases the coupling. This is the second part of the experiment. This emphasizes on electric field shielding. In the electric field shielding, we have an experiment where you have the network analyzer. The network analyzer goes from 5 to 12 megahertz. We are measuring the coupling S to 1, and I think we have 3 dB division in the vertical. As test objects, we have a metal disc. The metal disc is only connected to the inner conductor of the coax, so the shield of the coax is not connected here. So we have two discs, and they have a capacitance between each other, and they have also, of course, capacitance to ground. And via these capacitance, the energy can be transferred from one side to the other. And we can insert different objects there to see how the shielding effect is. Now, if we take a piece of cardboard, this is just cardboard, we see pretty much no effect, which is not a surprise because the cardboard is not a conductor. So in the previous video, we've used this ring, metal ring, with an opening, and we had seen that the magnetic field shielding doesn't exist if the ring is open. Only if it's closed, the current can flow. Emphasizing again, for magnetic field, we need really low impedance so the eddy currents can flow well. Now let's insert this ring. This ring is not connected to me in here. And we see a very, very, very small shielding. Now if I connect the ring to the connector, we see a significantly larger shielding because the capacitance which exists from the disc to the ring causes a voltage here, but if I contact here to ground, the voltage is shorted. Even if I just take my wet fingers, we see a significant shielding, emphasizing again that for electric field shielding we just need a relatively high impedance path to ground. We can do the same with the disc in styrofoam. The disc in styrofoam has a relatively low shielding. Now if I connect the disc, I just use this as a connector. If I connect the disc to ground, we see a very good shielding because the voltage induced on this plate is shorted to ground. And if there's no voltage, then the capacitance from here to here will not see any current flowing. Do another experiment. We put this electric field experiment, we put paper towel in. It's dry paper towel. And the only effect which we see is caused by the proximity of my arm. So the paper towel has in principle no effect. Only my arm has an effect, of course. Now let's make it wet, the paper towel, to see if the conductivity is enough. So now we have wet paper, dripping wet paper towel. You know, it has a very small conductivity, but it's enough for electric field shielding. We hold it in between and we see a significantly larger reduction compared to the dry paper towel which we had before. This emphasizes again that the electric field shielding, we only need relatively high impedance current paths to guide the induced current to ground. Okay, we have just explained or showed you the experiment. Now let me show a little bit on a circuit level some of the background. So we have these two discs, the metal disc. They're simply connected to the inner conductor of this coax cable. So if you think about this as being a circuit, here is the transmitter side of the network analyzer. Voltage source 50 ohm, coax cable connected to one of the discs. The other side, the disc connected coax cable to 50 ohm. So if we draw some field lines in, electric field lines, we'll have field lines connecting one side with the other. And of course there's a voltage on here, so we have some field lines going to ground. This side is terminated with 50 ohms, so the voltage is very, very small, so we pretty much have no field lines going to ground. We can express the electric energy in the electrostatic field or on the low frequency field by capacitors. And this is always possible as long as the structure is electrically small, which means that the structure, the distances are much, much smaller than the wavelength, which is the case here. So we have a capacitance from here to here. We have a capacitance from here to ground. There's a capacitance inside the coax cable. There's a capacitance from here to ground. And there's, of course, a capacitance inside the coax cable. Now, if we insert a piece of metal here, we will come to an equivalent circuit where we have a voltage source, a source impedance, we have a capacitance, then we inserted a piece of metal, and then we have a connection on the receive side. This is Rx. So this equivalent circuits for the case where we have the transmit, the receive side, and the metal piece in the middle. Yeah? And if we look at the capacitance values are very low. These are like single picofarad. Now, in this case, this is not grounded, so the path from here to here is unhindered. So, but if we ground this via a very high impedance resistor, and even 100K would be enough, then because of the low values of this capacitor, the current will mainly flow to ground here, and the voltage here will approximately 0. So even 100 kilo ohm would be a very, very good shield for the electrostatic case. How do the field lines look like when we insert a piece of metal? So now I insert this piece of metal, and the field lines, this is not grounded right now, so the field lines will simply go to the metal and continue from the metal. Of course, there may be one field line going to ground. But in overall, the field line structure is not changed a lot by inserting the piece of metal, because the piece of metal is perpendicular to all the field lines. The moment we ground it here via a high impedance resistor, the voltage pretty much goes to 0, and these field lines, of course, disappear, and the systems are decoupled. The shielding is very successful. I want to emphasize again that in most shielding problems we can understand what's going on by simply thinking that the total field is a superposition, a linear superposition of the initial field and a reaction field. So a plane wave comes, the plane wave hits metal, in the metal there's current flowing, the current causes a field, and now the field left and right of the metal is basically the superposition of the reaction field, or some people call it scattered field, and the initial field. And this concept works for high frequency shielding, that concept works for electrostatics, it works in many cases.